Hello and welcome. My name is Amar. This is Data Structures and Algorithms, a course for computer science undergraduates. This is lecture 1 and we are starting from the very beginning. I'm going to assume you know nothing about this subject yet. If you can count and you have written even a few lines of code, you can follow this. Here is the question the whole course answers. A computer holds a pile of information. How should we arrange it so the things we need are quick to find? That question sounds small, it is not. The wrong arrangement can make a program a million times slower. By the end of this lecture, you will be able to do 4 things. First, explain what memory actually looks like. Second, explain what a data structure is precisely. Third, describe an array and a linked list and say when to use each. Fourth, measure the cost of an operation using big O notation. Nothing in this lecture requires you to memorize anything. Let's begin. Let us start with the smallest possible question. What is data? Every program does 2 things. It stores information and it acts on that information. The information is the data. A score in a game, a name in a contact list, a price in a shop. Underneath, a computer stores all of it the same way, as numbers. And it writes those numbers using only 2 symbols, 0 and 1. One of those symbols is called a bit. Think of a bit as a switch that can be off or on. One switch gives you 2 possibilities. 2 switches side by side give you 4. 3 switches give you 8. Every switch you add doubles the number of possibilities. Line up 8 of them and you get 256. 8 bits together are called a byte. So 1 byte can hold any whole number from 0 to 255. Now here is the part that surprises people. Letters are stored as numbers too. There is simply an agreed table that says which number means which letter. In that table, capital A is 65. Capital B is 66. Capital C is 67. The letters are not really in there. Only numbers are. Which leads to the first big idea of this course. The same bits can mean completely different things. What decides the meaning is how we agree to read them. Now, where do those bytes actually live? They live in memory. And memory is simpler than most people expect. Picture an enormous row of small boxes. Each box holds exactly 1 byte, and each box has a number painted on it. That number is called its address. Think of a very long street where every house has a number. The house number is not what is inside the house. It is how you find the house. Memory works the same way. The address tells you where, the byte inside tells you what. Now, the property that everything in this course depends on. If I give the computer an address, it can go there immediately. It does not walk past the other boxes to get there. Reaching box number 1 million costs the same as reaching box number 5. That property has a name, random access. Random here does not mean unpredictable. It means any box in the same amount of time. And a variable, the thing you write in your code, is just a name. A friendly name for one of those addresses. So we have data and we have somewhere to put it. Now we can define the thing this course is named after. A data structure has 2 halves. The first half is the layout, how the values are arranged in memory. The second half is the set of operations, what you are allowed to do with them. Both halves matter and most people forget the second one. Here is why the arrangement changes everything. Imagine a shopping list written in the order things occurred to you. To check whether milk is on it, you read the whole list. Now imagine a phone book sorted alphabetically. To find one surname, you do not read the whole book. You open it near the right letter and narrow down. Same information in both cases. Completely different amount of work. The only thing that changed was the arrangement. Let us build the simplest data structure there is, the array. An array stores values one after another with no gaps. Every value has the same type, so every value takes the same number of bytes. Say we are storing whole numbers and each one takes 4 bytes. The first one sits at some address. Let us call it the base address. In our picture, the base address is 1000. The second value starts 4 bytes later at 1004. The third starts at 1008. Can you see the pattern forming? Here is the formula, and it is the most important line in this lecture. The address of an item equals the base address plus its index times the size of one item. Let us use it. Where does the item at index 3 live? 3 times 4 is 12. 1000 plus 12 is 1012. And that is the answer. 1 multiplication and 1 addition. Notice what we did not do. We did not look at the items before it. We did not search. We calculated. So reading any item of an array takes the same small amount of work, no matter how enormous the array is. That is why arrays are everywhere. By the way, this is why indexes start at 0. The first item sits 0 steps from the base address. Now, the other side of the coin, an array is fast to read and awkward to change. Suppose we have 8 values and we want to insert a new one in the middle. There is no gap to put it in. The values are packed shoulder to shoulder, and that is the whole point. So to make room, every value after that position has to shuffle along by 1. In our example, that is 4 values moved to insert 1. And if we insert at the very front, every single value has to move. So the cost of inserting grows with the size of the array. There is a second problem. An array has a fixed size decided when it is created. If it fills up, we must build a bigger one and copy everything across. So, reading is cheap and rearranging is expensive. Hold on to that sentence. We are about to invert it. Here is a completely different way to arrange the same values. It is called a linked list. In a linked list, the values do not sit next to each other at all. They can be scattered anywhere in memory. Each value is wrapped in a little package called a node. And a node holds 2 things. It holds the value itself, and it holds the address of the next node. That second part is called a pointer because it points at where to go next. So the nodes form a chain. Each one tells you where to find the one after it. The last node points at nothing, which is how we know the chain has ended. Now watch what happens when we insert into the middle. We create the new node. We point it at the node that used to come next. And we point the previous node at our new one. 2 pointers changed and we are finished. Nothing shuffled along, nothing was copied. It costs the same whether the list holds 10 items or 10 million. But now ask for the item at position 5. There is no formula anymore. The nodes are scattered, so we cannot calculate where the fifth one is. We have to start at the front and follow the chain, one node at a time. So reading by position is now slow. One small extension you will see often. Give every node a second pointer back to the node before it. Now the chain can be walked in both directions. That is called a doubly linked list. It costs a little more memory per node, and it buys a lot of convenience. Put those two structures side by side and look at what happened. The array reads instantly and changes slowly. The linked list changes instantly and reads slowly. The trade is exactly reversed. So which one is better? That question has no answer, and asking it is the mistake. The right question is, what will my program actually do most often? If you mostly look things up by position, use the array. If you mostly insert and remove, use the linked list. This is the central idea of the entire course. You are not looking for the best data structure. You are looking for the one that is fastest at the thing you do most. Before we can compare properly, we need one more thing to compare. So far, we have looked things up by position. But usually we want to look something up by value. Is the number 42 anywhere in here? If the values are in no particular order, we have only one option. Start at the front and check each one at a time. This is called linear search. If we are lucky, it is the first item and we stop immediately. If we are unlucky, it is the last one or not there at all. Then we have checked every single item. So with 1000 items, the worst case is 1000 checks. Now let us change one thing and one thing only. Let us sort the values first. Now we can do something much cleverer. Jump straight to the middle item and compare. If our target is smaller, it must be in the left half. If it is larger, it must be in the right half. Either way, in one comparison, we just threw away half the data. Repeat that on what is left and throw away half again. This is called binary search. Let us count it. 1000 items cut in half. 500, then 250, then 125. Keep going and you reach a single item after about 10 steps. So linear search needs 1000 checks and binary search needs 10. Double the data to 2000 items. Linear search now needs 2000 checks. Binary search needs 11. Doubling the data added a single step. That is what people mean when they say sorting pays for itself. Which means we need a way to talk about cost. And we cannot just time it with a stopwatch. A fast computer would flatter a bad structure. So instead of measuring seconds, we count operations. And we count them as the amount of data grows. We call the amount of data the letter n. Reading one item from an array takes the same work regardless of n. We write that as big O of 1 and we say constant time. Walking a linked list from the front might touch every node. That is n operations. So we write big O of n and say linear time. Now, why do we throw away the details? Suppose one method takes 2n plus 30 operations. When n is 10, the 30 matters more than the 2n. But when n is 1 million, the 30 is a rounding error. Big O keeps only the part that dominates as the data grows. Let us see why that is worth doing. Compare a linear method against a quadratic one, which we write as big O of n squared. With 10 items, one takes 10 steps and the other takes 100. Annoying but survivable. With 1000 items, one takes 1000 steps. The other takes 1 million. With 1 million items, one takes 1 million steps. The other takes a million. That is not slower, that is impossible. And there is one more you will meet constantly. Big O of log n, logarithmic time. That is what you get when every step throws away half of what is left. Searching a sorted phone book behaves like this. To search a million names, it needs about 20 steps. So the order to remember from best to worst is this: constant, logarithmic, linear, and finally quadratic. One last piece of vocabulary, and it is one professionals use daily. We separate what a structure does from how it does it. The what is called an abstract data type. It is a list of the operations and nothing else. For example, a list must let you add an item, remove an item, and read one. That description says nothing about memory. The how is called the implementation. And we just build two different implementations of that same list. The array and the linked list. Same promises to the outside world, very different costs inside. Now let me save you from a mistake almost every student makes. Having heard that inserting into a linked list is constant time, people conclude that linked lists are simply faster. They are not, and here is the catch. Inserting is only constant time once you are already standing at the right node. Getting to that node means walking the chain, which is linear time. So inserting at a position you have to find first is not cheap at all. There is a second reason, and it is a practical one. Real processors fetch memory in blocks, not one byte at a time. An array is packed together, so those blocks arrive full of useful data. A linked list is scattered, so the processor keeps fetching blocks it barely uses. This is why in practice arrays often win even where the theory says otherwise. Big O tells you how something grows. It does not tell you everything. So where does the course go from here? Next, we build structures with rules about the order things come out. Stacks where the last thing in is the first thing out. Queues where the first thing in is the first thing out. Next come trees, which let us search in logarithmic time. Then graphs for anything shaped like a network. Then hash tables, which get lookup down to constant time. And the algorithms that run on all of them. Let us summarize what you now know. Memory is a numbered row of cells, and any cell can be reached instantly. A data structure is a layout plus the operations allowed on it. An array stores items next to each other, so it can calculate any address. That makes reading constant time and inserting linear time. A linked list stores nodes anywhere joined by pointers. That makes inserting constant time and reading linear time. And big O notation lets us compare them honestly as the data grows. Here is your exercise before the next lecture. Take a list of 100 numbers on paper. Count the moves needed to insert a value at the front of an array. Then count the moves needed to do the same in a linked list. Write both answers down, that is big O reasoning done by hand. In lecture 2, we build the stack and the queue. My name is Amar. I will see you in the next lecture.